Yeah, Joel Lindegaard, and you can see that Damla is also a co-author and a bunch of other folks in my group. So he should be presenting it, but he couldn't attend in person, and Leonid required me to present in person because we'll have remote presenters later on. Okay. Yeah, I can see that. Yeah, he's making us do a lot of work, as you can see over here. Okay, so this is not working. So maybe I'll go back to here. No. Okay, sorry. Okay, that's much better. Wait a second. Something is not working over here, so I'll have to go back. Okay, so I think I'll stay here. So essentially, this work is about pairwise alignment. Pairwise sequence alignment is a recurring kernel in many genomics workloads, including read mapping and de novo assembly. And this is often the bottleneck in these applications. I'm going to give you some results, and the paper has some results also. But before that, I'll give you an introduction to Jainism, which is better done by Damla. So if I do a bad job, she'll tell me. Essentially, Jainism is the work that we're going to build on. It's proposed in Micro 2020, and Damla mentioned this. But basically, the idea over here is to use bit vectors to build the dynamic programming table. And this extends the BiTAP algorithm, which I'm going to mention briefly, but I'll not go into a lot of details. And it also adds traceback operation to it. Basically, you can see that the dynamic programming table is really based on bit vectors. We're going to talk about that a little bit. And if you're really interested, you should really read the Jainism paper because there's a lot of detail on this, or talk to Damla. I hope she remembers. Okay, so that's the paper. So what did we do in that work? I think Damla presented last year. Is that correct? At the AACBB. So I'll quickly overview that. Essentially, our goal was to extract approximate string matching by designing a hardware-friendly, fast and flexible framework that also can extract multiple steps of the sequence analysis. And this was the first ASM acceleration framework for genome sequence analysis. As I said, this was built on the BiTAP algorithm that was proposed in the 1990s. And this algorithm is nice. It was actually proposed for fast text searching, which is essentially what we're doing in genome sequencing, right? And it uses fast and simple bitwise operations. But it was not enough for what we needed to do, so Damla extended it to make it highly parallel. And also, she needed to add traceback to it so that you can actually get the edit distance. And essentially, Jainism introduced a way of designing the algorithm and accelerator so that you can accelerate it with nice hardware. And this is the hardware. Again, I will not go into a lot of detail, but this part over here does the distance calculation, essentially generates the bit vectors, and then it feeds that to this traceback SRAMs, which is going to be one of the things that we're going to target in Scrooge. We're going to try to reduce the size of it as one of the contributions. And then the traceback accelerator is a specialized hardware that does acceleration. And if you're interested in how these are designed, they're in the Jainism paper. The distance calculator is essentially a systolic array that does the distance calculation as dictated by the modified BiTAP algorithm. And the traceback calculation is essentially does traceback and cigar string computation. Okay, and then Damla evaluated this in detail, and we actually collaborated with Intel in terms of some of the area and power and other evaluations. But we showed that this is actually not bad in terms of area and power overheads. And it has a bunch of use cases that we have discussed in that work. I will not go into a whole lot of detail over here because I want to focus on Scrooge. But essentially, you can accelerate read alignment in read mapping, and you can use it as a pre-alignment filter. Or you could do edit distance calculation. And there are also other possible use cases that could be done, as I mentioned, like text search could be one, but also there are other interesting cases which could accelerate assembly, like read-to-read overlap finding, etc., which I think is quite interesting. So there's a lot of opportunity for those people who might be interested in looking for research areas. So there are a bunch of key results, which I will again not go into detail, but basically the results were good at the time. You get significant speed up compared to both software accelerators as well as hardware accelerators. Designed for different purposes, as you can see. Yeah, I'll let you read the paper or watch Damla's talk from Micro. Maybe the AACBB talks are online too. I don't know. I haven't looked. Okay, so what's Scrooge basically? If Jainism is so good, what did we do? Essentially, Scrooge is a faster and more efficient version by re-examining the algorithm, and also it adapts Jainism to multiple different computing platforms. So our goals were, this is actually Joel's master's thesis. He worked very closely with Damla, and then he later became a PhD student. But he actually did a lot more work after he finished the master's thesis to make this a strong publishable work. So basically, our goal was to build a practical and efficient implementation of the Jainism algorithm for multiple computing platforms. Initially, we started with GPUs, but it got extended. And we wanted to compete with state-of-the-art pairwise sequence aligners like EDLib, KSW, and also WFA and BiWFA later on, which are quite interesting works. Essentially, what Scrooge introduces 3 new algorithmic improvements, which address particular inefficiencies in Jainism. And we have open source implementations on CPUs and GPUs. And the key results are actually better than Jainism. So on top of the improvements that I showed you with Jainism, you get significant more improvements in terms of in CPUs, GPUs. And also you get good area efficiency compared in ASICs. Okay, I'm going to show you some results. So I'll skip some of the background since this workshop is clearly, these are Joel's slides. So when he introduces them, he uses background. So I'm going to skip them because I think this workshop is clearly aligned with accelerating genome analysis and the goals of it. Clearly, we are bottlenecked in some of the computations we do. And in this case, we're looking at read mapping. So read mapping consists of many steps: indexing, the reference genome, and then seeding, and then pre-alignment filtering, which has multiple different types of algorithms, and then read alignment. Okay, so this is a breakdown from a relatively recent paper that looks at long read analysis, and I'd recommend people to look at it if you're interested. And you can see that read alignment is often the bottleneck in read mapping, especially for long reads. So essentially, pairwise sequence alignment, which may have already been discussed in earlier talks also, you compare a pair of strings while allowing some sort of edits, essentially. So what are edits? Edits could be substitutions or mismatches, insertions or deletions, essentially. So if you compare these 2 strings over here, you can see that there are 2 mismatches or substitutions in those locations. And then you can see that there's an insertion in Safari that doesn't exist, in Salami. And then you can see that there's a deletion over here. And then eventually, by doing this, you come up with what's called a cigar string. That's the output of the pairwise sequence alignment. So how is it done today, sequence alignment? Usually you use some sort of dynamic programming algorithm. There are many different versions of it. And more recently, WFA actually improved on this. So there's actually interesting algorithmic improvements that are happening over here. And usually these algorithms build a dynamic programming table comparing the 2 strings. And when actually you need to compute differences, you calculate the next entry in the table using the values of the 3 neighbors using arithmetic operations, which are clearly doable in hardware, but expensive. So what Jainism did essentially is to replace this table with bit vectors. So it's maybe in terms of size, it may grow a little bit. I don't know, as we will see. But if you see that how the calculations are done, now the calculations are not arithmetic operations, but they're bitwise operations, simple bitwise operations, bitwise and or XOR, and also shift. Okay, this particularly efficient hardware. And that was actually the reason why Damla started examining BiTAP, because it was quite interesting from a hardware perspective. Damla, please correct me if I'm wrong. Okay, so again, I don't want to go into a whole lot of detail, but you need to trace back once you form the dynamic programming table. You need to trace back so that you can figure out exactly how many substitutions, how many deletions, how many insertions you have when comparing 2 strings. So traceback actually happens in this algorithm by searching for the leftmost column for the topmost 0. So this is actually what you have, essentially one edit. And the row number is the edit distance over here. So essentially, by tracing back this table, by backtracking the origin of the topmost 0 in the table, you figure out the cigar string. Okay, so let's take a look at what are the inefficiencies of Jainism. Essentially, Jainism was built for ASICs. And the question is, can we do better? So we also wanted to actually adapt this to CPUs and GPUs, because clearly ASICs are not easily adaptable. And that was the other question we asked, basically. Can we do better than Jainism on an ASIC implementation? And can we actually apply it to commodity hardware? I think there should also be an FPGA over here, but we didn't have enough time, let's say. I think that's also quite interesting. Maybe Damla has thoughts on that. Okay, so essentially, one of the questions that we also looked at is, do we have enough memory bandwidth for the Genasm algorithm. So we did the roofline analysis on CPUs and GPUs. You can see that the Genasm algorithm lies over here. So this is throughput on the y-axis, higher is better clearly. And this is the arithmetic intensity or operational intensity. And Genasm happens to be over here. You can see that it's bound by memory. So our desired operating point is utilizing the peak computing throughput that you have in CPUs and GPUs, but we're falling short, as you can see. Okay, so this is actually happens if the data resides off chip. Okay, I think that's clear. Basically, Genasm cannot saturate the commodity hardware with computation due to limited bandwidth or too much data movement. So can we do better? Essentially, can we have enough on-chip memory for the Genasm algorithm so that we don't go off-chip? That was one of the questions Joel tackled. So if we do some analysis on CPUs and GPUs, these are the memory sizes of the particular implementations we examined, L1D size and the shared memory size for the GPU we looked at. And we looked at the memory footprint of the Genasm algorithm, and we see that memory footprint is larger than the L1 cache, so you actually get a lot of cache misses on the CPU. And here, memory footprint fits in the shared memory. Unfortunately, this is for a single thread. So once you start utilizing multi-threading, these caches as well as the shared memory becomes too small. And the goal was actually to minimize this memory footprint. That's the first thing, or that's the second thing, sorry. That's the second inefficiency. We have a large memory footprint, especially when you have multiple instances, which you do in hardware multi-threading. Okay, then the next inefficiency is unnecessary work. And this is actually a lot of, I think, interesting works tackled not building the dynamic programming table these days, or not doing the computation that's needed for traceback as much as possible. And this is essentially what we're also trying to do over here. Once you essentially find the zero that happens leftmost on the over here, you don't really need to compute any part of the table over here, essentially, because it cannot be reached by traceback, and you know that because you found the zero over here. This is essentially based on the properties of the Genasm algorithm. Again, Damla, please correct me if I'm wrong. Okay, so that's the inefficiency. There's a lot of unnecessary work that is done because there are some cells that are computed even though you cannot reach them by traceback. Okay, so this is the summary, essentially. We have large memory bandwidth requirement, large memory footprint, and large on-chip memory footprint, I should say, and then unnecessary work. And Scrooge essentially introduces 3 optimizations to fix these. It introduces 2 memory improvements and 1 efficiency improvement. To reduce, the memory improvements are there to reduce the memory footprint and the data movement. I'm going to give you a very high-level descriptions of these. Hopefully, they'll be intuitive. And then the source code is actually online. You can actually try it for yourself. So let's talk about the first one, Sene, which is store entries and not edges. Well, maybe before we talk about that, the overall benefit when these are all combined is a 12x reduction in the memory footprint and data movement, and no unnecessary work. Essentially, we could eliminate the unnecessary work, at least the way we defined unnecessary work. There could be other unnecessary work, of course, that we may be missing. Okay, so let's talk about the store entries, not edges. This is a simple idea, although it wasn't implemented in Genasm. Essentially, if you look at what Genasm stores when you compute this table, it stores these edges over here, which is a lot more information than storing the entries. So essentially, Scrooge stores entries, and it has some algorithmic changes to make this work. And this leads to a 3x reduction in memory footprint and data moments, as you can see, right, which is good. And the next one is not storing the entries that are not used by traceback. So as we discussed, traceback is confined. Well, we didn't discuss it, but you'll have to take my word for it. Essentially, traceback is confined due to some windowing heuristics that we used. Essentially, remaining bits over here can be computed, but they don't need to be stored. So this actually gets rid of the storage that is otherwise done in Genasm. And this also leads to about 4x reduction in memory footprint and data moment resulting. Okay, and the last one is essentially terminating unnecessary work, as I mentioned earlier. Essentially, you can stop building the table as soon as you find a zero over here. And then you can start traceback immediately without building the rest of the tables, because the rest cannot be reached by traceback. And this, again, on average, at least 25 cells are unnecessary. Of course, this depends on your data set. And you can find the data sets we use online also. Okay, So essentially, these improvements were implemented on both CPUs and GPUs, as well as ASICs. And these are open source. CPUs and GPUs are open source. If you try it, please let us know. We've received a lot of feedback, actually, after we put it online. And Joel was very good at answering that feedback. So CPU version, I'm not going to go through this in detail, but essentially, they're programmable. And you can find on GitHub over here. Okay, let's talk about some results before we conclude. Essentially, if you look at long reads and short reads, you can find the methodology over here. And we use some good enough CPU, let's say, and a GPU. And we also have the ASIC process, very similar to Damla's Genasm work. So let's look at long read throughput. This is alignments per second, essentially throughput. Higher is better, of course. And on the CPU side, we compare to a bunch of different algorithms over here. You can see, including WFA, KSW, EDLib, and Genasm. And the throughput results that we see is much better compared to the best prior works over here. And the GPU results are similar. These are the GPU algorithms that we were able to run. And you can see that that improvement is also significant. Okay, that's a summary of the results. And short read throughput, essentially the improvements are there also. But in this case, WFA actually does quite well on the CPU. But there's still some improvement over here. And the GPU is also improvement is significant over Genasm. So comparison point, even though we're trying to build on Genasm, maybe I should also say that compared to Genasm, we always improve. But we also tested to other implementations of other alignment algorithms, as you can see over here. Okay. So ASIC results, there's no significant computation overhead over Genasm ASIC. And on chip memory, as we said, the traceback storage, the traceback SRAMs get reduced because we don't actually store a lot of what Genasm stored. And you can see the numbers over here. You get significantly smaller chip area and significantly lower power. And there's more analysis of this in the paper, but I don't want to spend more time since you may want to ask questions. Essentially, the main improvements are really coming from the traceback SRAM memory footprint reduction. There's significant resource savings there. There's more in the paper. You can see basically the benefit of each of these improvements, either alone or together with different combinations, is studied in the paper. So all of these together actually improve performance the best. There's thread scaling results. I believe these results were with 48 threads, but I don't remember. You should ask. You should either look at the paper or ask Joel with it. So thread scaling is important, clearly. There's accuracy analysis, which is also interesting, I think. And there's sensitivity analysis of throughput and accuracy and the more detailed ASIC breakdown if you're interested. And again, the paper is online. We have an extended version on archive that we keep improving based on the feedback. We'd be happy to get feedback. Okay, so to conclude, we tackled the pairwise sequence alignment problem. It's computationally costly and it's used in a lot of parts of the bioinformatics pipeline. And Genasm is interesting because its ASIC implementation is significantly faster than prior software aligners. And our goal in this work was to build a practical and efficient implementation of Genasm by on multiple computing platforms, also overcoming its prior inefficiencies that we found, and also to compete with state-of-the-art sequence aligners that are also designed for CPUs and GPUs. And as I mentioned, there are 3 new algorithmic improvements that address Genasm inefficiencies, and we have efficient open source CPU and GPU implementations. And you can see the summary of the results over here. We get significant speed ups over Genasm on CPU and GPU, and you get better area efficiency over an ASIC implementation. And there's also, compared to other state-of-the-art sequence aligners, there's speed up over both CPU and GPU platforms. So I'll stop here. Happy to take any questions. But if you have any really deep questions, you should ask them to Joel, because he is the one who did the work. Yes, Chris. Yeah, I mean, I think this is a good question. And again, I don't know every use case of bioinformatics pipelines, but when we talk to people, they like the edit distance metric. It's a metric they can empathize with and they can quickly figure out. So I cannot completely answer your question, but I think these tools are used. Well, for example, I think edlib is used, for example, in some of the tools. Maybe Damla can answer this better in some bioinformatics pipelines. So I believe there's a role, but I clearly cannot tell you like how widespread it is. Damla, do you have any comments on this?
You can use this.
Yeah.
Like other use cases, more than other use cases, I can talk about Scrooge and Jainism as well. So we try, yes, they are based on edit distance, but we try to enhance them so that they can act like different like non-edit distance like scoring as well. So they are not 100% matching that's like scoring schema, but at least we have an attempt to let them support that as well. And that's what the accuracy analysis in both papers, in both Scrooge and Jainism reflects. But you are right, it is not highly used in like in-depth analysis for like alignment as part of alignment. But yeah, EDlib is, for example, one that is being used in several occasions. But yeah, it's not as highly adopted as the other ones because they are limited. You're right.
Yeah, but I mean, I think I should also say that adoption is a combination of many factors, right?
Yeah.
It's not just because a metric may not be useful. It's also like when did you develop your tool? That also has an impact on adoption.
Yep, sure.
Exactly.
Yep.
Exactly. You're doing a lot of data movement.
That's right.
I want to ask about so we have the bit vectors here. We use them for pairwise alignment. Compared to the dynamic algorithm that we use, for example, in Needleman-Wunsch. So is it, I mean, does it need more area to, to do those calculation? I mean, for the bit vectors, can we say that, I mean, it needs more, I mean, at least more space or area to do the calculation for the bit vectors?
More area just for the compute logic?
Yes.
So I mean, maybe Damla can answer this better, but I don't think so. I mean, it's much more simple. These bitwise operations are much more simple than additions, for example, that you need to do with arithmetic operations. But I mean, Damla may have an exact number that I don't remember off the top of my head.
Yeah, I wonder that. Yeah, because you talked about no need work. Yeah, I mean, you're just reducing that to make it comparable.
Yeah.
Okay.
Yeah, exactly.
Okay. Yeah. Okay. Thank you.
So I think once you go into the bit vector type of representation, it's much more, let's say, suitable for hardware.
Any more questions? No? Well, let's thank Onur again.
Okay, thank you.